officially in air.
We
Hello.
are.
Cool. Hello, everybody. Hello, ladies and gentlemen. It's me, Artem, the main co-host from Immunefi side. We also have Tim from Hacker Success. He'll be our co-host today. We have
Hello.
glorious Adrian as a listener. And we have Fuel Network team with us to help you with getting familiar with the Fuel code base and so you can successfully participate in the hackathon that will start very soon. Okay, so let's wait maybe a couple more minutes so more people will join, and after that we will start. Fuel team, maybe you can, while we are waiting for all the people to join, maybe you can introduce yourself a little bit.
Hey, I'm Brandon. I'm the CTO of Fuel, and with me today I brought several team members who can walk through different parts of our code base. So we have Green, who will be walking through the VM and the node itself. Rafael, who'll be walking through the bridge and the contracts that we use for that. And we also have Igor from the compiler team to explain how Sway is working.
Cool, thank you. So I think it's officially the time to start. So let me just go very briefly through the Attackathon that will start in 10 days and 17 hours. So it'll have the max bounty of $1,300,000, which is kind of an impressive number. Yeah, it will start on 17th of June and it will end on the 22nd of July. The rewards will be paid in USDC. It will be trashed by Immunefi, and if you find a valid bug, you'll be required to go through the KYC process. And we have an impressive amount of lines of code to go through. It will be capped at 100,000. So you can, if you need more information on this, you can find more information on the Attackathon page itself on our official website. And okay, so now we're good to go. So Fuel team, maybe you can go over the topics that we will cover today so our audience can identify what exact information we will be discussing today.
Sure. Thank you, Artem. Yeah, so I'm just going to kick this off with a quick, short presentation and then hand it off to the different representatives from different teams to walk through their areas. So let's see if I can share. All right. Does it look like my screen sharing is working?
I actually cannot see it.
Okay. Let's see, because I see it in the stage now.
Yeah, I can see it.
Technical overview.
I can see it too.
Oh, and I also can see it right now.
Great. Yeah, so I think the big things to talk about here are, what makes the fuel stack and fuel ecosystem different than Ethereum, and what is the main stuff to look at, what are the interesting areas that you want to dig into. So as a quick intro, we made our own VM. We call it Fuel VM. And some of the big features about it in terms of its architecture are that it's register based, which makes writing different kinds of IR or doing static analysis on bytecode a little bit easier, and certain kinds of optimizations a little bit more straightforward. They have 64-bit words.
Excuse me, but we still cannot see the screen.
Oh,
it also disappeared from me. Maybe you can try and reconnect.
I think it'll kick me off the stage, but I can
Yeah.
maybe send the slides to Green and he can
Yeah.
share. 'Cause, like he was able to do that.
As always, some of the people can see it, some of the people cannot see it.
Yeah, I also can see your screen. So
With Discord streaming, it's always a gamble.
Well, I agree. If you want to give it a shot, maybe more people will see it. See what's the chat saying. I can't see anything. It's just loading. You can see it.
I
can't
requested access.
see it. Sorry for this. Wait. Alright, Green. You should have access to it now. If you want to give it a shot to share, maybe more people will see it. It's weird that only some people could see it and some not.
Just in case we still will be recording the screen and you'll be able to watch the recording. I think it will. Pepin said that it will be available this afternoon. So in case it won't work, just know. In any case, if you want to like rewind all the info we will go through today, you'll be able to watch the recording.
It works.
Oh yeah,
Okay,
now
I can
it's
see.
working.
I can see
and
Green's sharing.
1440p, nice. 60 FPS, also nice.
Yeah, we're finding bugs in Discord now.
Bad that they
Okay,
don't have
so
a bug
Green is
bounty with
joining.
Immunefi.
Yeah. Green, so do you want to switch to the slides? I'm just seeing your Discord screen.
Yeah, same here.
So you still see my Discord on the Discord, yeah?
Yes.
Mhm.
Because I'm sharing another screen. Okay. Let me try to share entire screen.
Yeah, now we see it.
Great.
Okay.
Yeah. So there's not a lot of slides here because we're just gonna try and dive into the code quickly, but hopefully this gives you guys kind of a good sense of what's different between us and like something like the EVM. So we have like I said, register-based VM. We use 64-bit words and 32-bit instructions. Part of that is because we wanted to make field VM a bit more closer to the metal in terms of the native instruction sets available on most CPU architectures. So that gives us a little bit more performance, and you don't have to waste a lot of time if you're doing smaller arithmetic operations. And then we also have global read access between calls. I think EVM is starting to catch up on this with the temporary storage, but that's something that FieldVM has been designed with from the beginning. So that allows things like cheap branch C checks without needing to fall into contract state storage and things like that. We also have built-in native safe math at the VM level, so you don't really need to spend much gas or extra time on checking the results of certain math operations. And the other big part of the field VM is that it supports our UTXO model. And so I guess one way you could kind of describe field as a combination of both kind of concepts from Ethereum and concepts from Bitcoin. So the way I describe it is you have Ethereum style smart contracts, but you also have Bitcoin style predicates. And what this enables you to do is have things like account abstraction out of the box through the use of DTXOs. And you can also have, oh, we're getting this screensaver green. You want to move your mouse? You also have like multi-user transactions. So that could be things like off-chain multisigs, or you could have fee payer systems where other people can pay for your transactions for you. So there's a lot of interesting kind of parts of that model that opens up a big wide design space for developers. And yeah, so a lot of that's covered by the TXO predicates, and as the common analogy for that would be P2SH on Bitcoin. The biggest difference between how we handle that versus Bitcoin is we support full current completeness and the predicate level. So you can write for loops and kind of make your code more efficient, and it's a bit easier to write. You can just use our new language called Sway to build them. You don't need to write it in some kind of fourth stack or something. So yeah, do you want to go to the next slide, Green? So to make all this easier to use in a more cohesive way, we decided to build our own programming language. So it's inspired by Rust. It's not actually Rust, because we decided that Rust is, great systems language, but it's not necessarily solving all the needs of smart contract developers. It has a lot of extra things that can slow you down when you're writing single threaded or blockchain based kind of blockchain VM based applications. There's a lot of extra concerns that don't apply from Rust. So we can kind of simplify some of the hard parts of Rust and then add a lot of extra features that matter to smart contract developers. So some basic summary here is we have things like traits, generics. We have some types of the enums. We do register spilling, so we don't have that 16 local variable bottleneck like Solidity did. It can support zero cost abstractions. We have a big standard library, which allows you to even do things like hash maps in memory. We also have some safety checks built in. So things like checks affects interactions as part of the semantic analysis. And we have also nice facilities for stateless reentrancy protection using the global memory read access and contract calls. And Igor will dive more into how the compiler works and other things later, but this is just a high level summary. So Green, you want to go to the next slide? This is just kind of very simple view, but it's going to kind of get a lot more complicated from here. But at the very high level, there's two major important contracts on the Ethereum side. There's the message portal, which essentially is what allows you to deposit funds into our rollup. So this is how the bridge works. The messages are picked up by the sequencer, and then from there they can be spent to be used to mint coins and that kind of different kinds of assets and convert them into native assets on Fuel. When you want to do withdrawal, essentially what happens is there's a separate service called the block committer that periodically posts state routes back to the chain state contract on Ethereum. Currently, we have this set to every few hours. There's a state route posted. And then from each state route, you can create a Merkle proof to withdraw to enact any sort of withdrawals that happen within that last window. So it's kind of the high level, but Rafael will kind of go more into depth on this. Yeah, and then from there, we can talk a little bit more about the bridge flows, but I think Rafael might want to dive into that more. So I guess from there, You can skip to the last slide, Green. Oh, so this is ETH deposit. This is kind of a more broken down version of what I was mentioning earlier with the high level. So we have when we're bridging from Ethereum to Fuel, the ETH goes into the Fuel message portal that turns into a input message, which is a special type of UTXO in our sequencer. And that is spent within a transaction. You can use it just like any coin you'd spend for gas. Then we have and this is kind of the simplified flow. And then for bridging assets over, Rafael will walk through that. And Green, you want to just go to the next one? And for simple ETH withdrawal, for the base asset, it's this kind of shows some more steps here. So essentially what happens is there's a special opcode in the VM that creates a receipt indicating the withdrawal. And that opcode is called send message out. And then all those receipts are collected into our block header, into one Merkle tree there. And then those headers are committed to the chain state. And then when you want to withdraw, you create a Merkle proof of that receipt on Fuel on the Ethereum side to claim those funds out of the bridge. Next slide. This is a quick high level of some of the repos. We can send these links out after the call, but they'll also be here on the recording. And yeah, from here, I guess maybe Green can start with the Fuel VM code walkthrough.
Can you hear me?
Yeah.
Yes. And maybe you can focus on some novelties that you will implement, because I think that's the most interesting thing to hear about from somebody who was developing the thing, because all the novelties, whiteheads will not be similar with them, and the novelties, as you all know, can introduce some new bugs.
I'm not sure what novelties is.
Well, I'm actually talking about like the UTXO model, about the sway itself, about the Fuel VM, about the consensus parallelization.
Okay, then yeah, let's maybe say that because of let's say because we support the UTXO model, we basically transaction knows what inputs are and what outputs are. And for example, on transaction pool level, on mempool level, we already can know the ordering in which we need to execute transactions, and also we know the conflicting transactions. And based on that information, we simply need to iterate our transaction and we already have everything without execution. We can decide how do we want to schedule execution of those transactions, and that allows us to have built-in parallelization, because we can split transaction into batches, and based on number of threads what your machine has, execute them in parallel without any conflicts. While in the case of Ethereum, you don't know what your transaction will touch before you execute it. It is very nice in the case of multiple transfers. Network can support seamlessly a lot of transfers without any problems. In the case if we have, for example, one contract and that contract is super popular, then all transactions to that contract should be executed sequentially. But I think it's normal for contracts. Let's say it's like one nice feature. Another nice feature is that transaction itself contains a lot of information inside. For example, if we'll go to field tx, transaction, here we have transaction type. It has different variants, and just go to one transaction to see how it looks like. For example, script transaction. So yeah, we have small abstraction here. Like here we can see script body. Script transaction itself, it is chargeable transaction. So we have chargeable transaction and non-chargeable transactions. In the case of chargeable transactions, all of them has like policy, inputs, outputs, and witnesses. So policies allows you to customize your transaction and add some limitations like maturity, like when your transaction, starting from which block height your transaction is valid. Yeah, some limitation for witness limit. Yeah, how, because witness it is variable field, it means that it is not included into calculation of transaction ID. So yeah, it is malleable data, and because of that, anyone potentially bad block producer can change something inside of the data, and for that we allow you to set witness limit and several other fields that also should like help protect user from any malicious behavior from block producer side or from anyone at the middle between block producer and user. So inputs and outputs, yeah, like as we discussed, it's part of UTXO model, and inputs itself, for example, coin input has contains information about owner, amount, asset ID, transaction pointer. Transaction pointer, it's another thing. I will discuss about it later. But yeah, main idea is that transaction itself contains a lot of information, and and user has access to that information inside of predicates. Inside of script, of course, inside of contract. But main feature is inside of predicates, and because of that, user can iterate over fields of transaction and like verify some conditions that he needs. For example, he can check maturity, or he can check owner, or amount, or asset ID, and have some different I don't know, rules regarding when the transaction is valid and when it is not. What is also nice, and together with many different opcodes, like we support, of course, like basic set of opcodes what you need to execute a transaction, but also we provide access to more advanced crypto curves. Like, for example, you can try to use maybe something ZK related, or you can implement nice account abstraction, and easy integrate with any other chains. So yeah, that part is nice. Also, coming back to transaction pointer, when we build like one of our goals, what we try to achieve, that also any state should be provable, and we plan to support like clients and be able to generate proof for any kind of data. So because of that, some fields of transaction also exist to support that idea. And for example, transaction pointer can be used to verify that that transaction, but like transaction pointer, it is pointer to place where transaction was created, like block and transaction block height and transaction index. And yeah, like anyone can take transaction and verify that it's really included into the block there, and if it requires, he also can verify like state execution, any roots like state roots, balance roots, etc. Yeah, maybe regarding like from UVM and fuel core side, I think that's all features, but maybe Brandon has some ideas about other nice innovations. I don't know. That we support. Brandon, do you have anything? If not, I will go through the code base.
I think that was a good high-level summary. I mean, some of like the examples of things you could use predicates for can get pretty advanced. So from just going from basic multi-sigs, we're looking into all sorts of interesting use cases to things like predicate-based order books, where essentially different people can combine their inputs together on a transaction to fulfill trades. And the advantage of doing it through predicates is that it avoids that sequentialization problem that Green mentioned when interacting with smart contracts. Another interesting part is like the most common transaction type is a script, like what Green was showing. The reason why we have scripts is that it allows for multi-call out of the box. So you don't need to have some kind of proxy contract that is able to call multiple other contracts. The script allows you to do whatever you want at the user level at the time you decide to do something. So if you want to call a bunch of different contracts together for one particular transaction, you don't need to deploy a contract to do that first and then call that one function on that contract. You can just on the fly decide, to call 10 different contracts in a sequence here if you want to. So that gives a lot of flexibility for DeFi Legos.
Yeah, also coming back to possible use cases for predicates, because you have script data and predicate data inside of your transaction and also access to witnesses, like basically transaction itself can contain the state, like the state of something, and even like you can implement something without any state on the blockchain itself, because it can have transaction has its state. Anyone can prove that that state was part of transaction, and just next transaction we will use state calculate the state from previous transaction, etc. So if you want, you can create a stateless decentralized application, and in that case it will be much cheaper for user because it will be like parallelizable. Plus, if you don't touch any storage, it will be much cheaper because storage operations are the most expensive one. All other operations are very cheap. Okay, so here's a field VM repository. Basically, in that repository we have like a few VM. It is primary repository, primary crate folder that exists here. It contains interpreter. It is a few VM itself that knows how to execute transactions. Interpreter, it's here. Like initialization, guess logic, we split it opcodes into 5 subsets, like ALU, crypto related opcodes, some opcodes that change the flow of transaction. What else? Blockchain related opcodes, like for example, if you want to get access to block hash or block time. And one more, maybe let's go to specification. First, like we have a separate specification repository that defines how VM should work. And based on that specification, anyone can create his own VM, maybe not Rust-based, or have another implementation of that. And here we have part related to fuel VM, and here we have instruction set what we support. So, and here's those subsets that I mentioned, like arithmetic, logical operations, control flow operations. Oh yeah, memory. The last one was memory. Memory operations, contract instructions that somehow affect state or interact with contract. Like you can copy part of one code, of one byte code into another one, or you can load using LDC one contract into another one. And for example, you can create upgradable contracts if you want to. Here is definition, the description how all instructions should work. Here's implementation of them. Yeah, mostly in those folders there are tests that verify correctness of behavior. So yeah, interpreter is used to, yeah, as I said, execute transactions. So we use it to execute all kinds of transaction, like script transaction, create transaction, where create transaction allows you to upload bytecode into the network. Upload and upgrade transaction, but they basically for maintaining of the network. And since each chargeable transaction has inputs, and inputs may be predicates, we also use interpreter to execute predicates. And we have a context here that define what kind of operation is allowed during predicate execution and what is not allowed. So yeah, it's about fuel VM. All other grades, they are mostly some helpers, not helpers, like it is segregation of logic that still will be used by fuel VM. But also those grades are used not only by client team, they are also used by SDK. Some of them are used by compiler. For example, fuel ASM is used by compiler to decode and encode, let's say, opcodes. Here is their definition. Yeah, maybe some tests related to how to pack and pack them. So something like this. Also, we have fuel types that contains definition of some basic types, like here, like address, asset ID, contract ID, message ID, nonce, salt, some simple basic types that are used across all Rust-based projects with their encoding and decoding. Plus, here we also have fuel derive that defines canonical serialization and the serialization for types and transactions. About canonical serialization and deserialization, we still can read in our specification on transaction inside of transaction format. Here, like transaction ID. And what else we have? Yeah, fuel TX defines basically all supported types of transaction plus validity rules for them. If you will go here to transaction, you can see that transaction is invalid, and here a list of cases when transaction is invalid, and the same for each type of transaction. So fuel TX implements those rules, verifies them, verifies that user has correct balance, transaction fits all limitations, etc., etc. Fuel storage, it is mostly connector between fuel core and fuel VM. So there's several definitions for traits, and that's it. Fuel crypto contains basic crypto primitives, what we're using inside of SDK and fuel core, like all curves what we support, and I think basically that's it. And fuel Merkle, it is like definition for Merkle trees, implementation of Merkle trees. We have binary Merkle tree and SMT, sparse Merkle tree. We had some tree, but we removed it. So yeah, right now we have only 2 trees. If someone wants to play with that, you're welcome. And I think we can go to fuel core. So yeah, fuel core itself, it's a roll-up node that knows how to execute transaction. It also provides GraphQL API endpoint, what you can use to interact, to request some on-chain data or off-chain data. You can submit transaction through GraphQL API and subscribe for transaction statuses. It's like one entry point. Another one is P2P layer. First of all, if you will go to like main folder here is grades folder that contains all basic grades. Bin folder contains some binaries. Here is fuel core, like main one, that will what you will run or use to execute your transactions. But main is grades, and here is fuel core crate that again like combines all services what we have into one final fuel core service that you can run, subscribe for blocks. You have access to all other services that are available inside, like P2P layer or GraphQL API, and yeah, you can basically, if you will use that crate with Rust, then yeah, you can easily start your own node by using that crate and provide correct input parameters to connect any network. And here we have services folder that contains all our services that yeah, maybe let's go a little bit back and go to docs and diagrams. And not here. Architecture. Here is description of how architecture is done inside. And here you can see that we have different components, and we call them services, and they somehow connected to each other. Like, for example, maybe I need to increase it a little bit more here. So, for example, we have executor. Executor knows how to execute blocks. Basically, he knows how to do state transition functions from one block to another one, from previous to the current one. And for example, we have block producer who produces blocks, and the block importer who imports blocks from the network. And they are using inside executor to execute blocks. Like when block producer will create a block, block producer gathers all required information to produce block and passes that to executor. Executor executes that and returns an additional result that contains some modification to database, to storage, and block producer will later interact with other services, but we don't need to go there. And the same for block importer. Like when block importer imports block from the network, when after all validation, like that block is valid, header was signed by correct set of validators, block importer will execute blocks and update state of the blockchain. So here's the diagram of the architecture. Then let's go back here. And yeah, all the services from the diagram is here.
And I guess screen. I just wanted to do a time check because we still need to get through Sway too. So yeah, just try to wrap this one up quickly.
Okay. Yeah. So we have consensus model that is responsible for creation of blocks, deciding what consensus do we want to use to create a block. Executor, yes, I said executes block, and basically that's the main logic. We have upgradable executor. So our network also supports forkless upgrades, so we can upgrade the network on the fly with a new state transition function. And upgradable executor, it is wrapper around executor to support that functionality. Block importer basically imports blocks. Yes, sync service synchronizes blocks with other nodes through P2P. P2P, peer-to-peer service that basically interacts with all other peers in the network and shares the information about transactions, about blocks, and transaction relayer that basically monitors Ethereum for incoming events. Like Brandon mentioned, that when you deposit your message, it will go to a specific contract on L1, and we like Fuel core node monitors that contract on L1 and includes those events into state when they arrive after finalization of Ethereum network. And transaction pool, which is responsible for storing transactions, pending transactions until they are confirmed or removed. Transactions are broadcasted through peer-to-peer, and basically that's it. Yeah, we have some small additional subgrades here, like Fuel core client allows you to interact with it is Rust interface through GraphQL API for Fuel core. And I think from here mostly that's it.
Maybe jump to where the integration tests are, just people want to pick their own POCs.
And here we have a test folder that contains test helper, or what is this inside of integration test, and many tests here. So if you want to look into tests related to like synchronization, for example, we have sync arrest that contains like 6 or 7 tests that verify that network can sync in different scenarios, like when there are some malicious actors or when everything okay. The same for transaction gossiping here. If you want to execute some opcode, you can use Fuel core. Again, to do that, maybe fee collection contract, not bad example of that, because we built a bytecode by using Fuel Awesome there. Or you can go directly to Fuel VM, and inside of Fuel VM, we also have Fuel VM benches, maybe not Fuel VM. Somewhere
there's a
here.
test folder inside of Fuel VM. Source tests.
Maybe. Okay, source. Yeah, and here we have all other tests where most of them are using opcode specifically. I guess maybe blockchain has, here you can find how to call contract, how script can call contract and call, for example, read-write operations there, how to, like at the end, how to verify those results registers. So yeah, regarding FuelVM SRC tests, main source that can help. And for Fuel core, Fuel core tests. Like messages, it's like how to create message proofs. That one, how to deploy your contract. With network, we discussed sync transaction gossiping. We also have regionality sync snapshot. It's other aspect of the network what we can do, but we don't need to go into that now. But if you want, you can check them as well.
Great.
And
I think we should probably cut to Sway. So Igor, do you want to take over?
Yeah, I'll take over. Thanks for the introduction, Green. So let me share my screen and to show you what we build on top of this, what Green was showing, and how the language works. Just a second. So share. Please just let me know if you can see my screen.
It's got two spinning boxes.
Spinning boxes. Okay, let's wait a while.
Yeah, it's not working again.
Ah,
It
that's
was working earlier.
yeah, it was working earlier where we were testing. That's inconvenient. Okay, let me try typical turn on, turn off thing. Just a second. Okay. Again. Crossing my fingers, asking you for the same.
Hey, it's working.
Can you see it now? Like the Visual Studio code?
Yep.
Perfect. So let's discuss this way a bit. The language built on top of this, on top of the Fuel
I can
VM, actually. Yeah.
I can see it, excuse me, but I'm not like I don't need to see it. But yeah, we have some audience that can see it too.
Mm.
Maybe Green can.
What-
Oh no, it would be impossible. Yeah,
It
maybe
would
you
be
can try.
difficult, yeah, jumping through the code and examples and so on and the pipeline.
Could you try to share the whole screen? Because when I shared also specific screen, it was not working.
Actually, I'm sharing this the whole screen. Yeah, that's usually the simplest option. Okay, just once again, stop sharing. And if I try to go for a particular window, yeah. Let's try our luck with a particular window.
Uh-oh. I think he crashed. Okay, well, I guess while we get Igor back, maybe Rafael, do you want to take on the bridge part?
Right, yeah, of course. Although I think that I cannot share my screen. I think the button is grayed out.
Oh, interesting. It's grayed out for me now too. It used to work.
Yeah, I think it bugged out.
Oh no.
Yeah.
It worked so well till this moment.
Right.
Maybe because Igor
Gents,
crashed.
can you try to rejoin the stage? I'll just like re-invite you to the stage. Maybe this will help.
All right. Yeah, I will do that. Back in a second.
Yep. Okay.
Welcome back, Green.
And Brandon back. Hey, Green.
It's still gray for me.
Oh, it's actually great for me too. Artem, can you join? Can you share anything?
Nope.
I wonder if we should restart the whole stage, the whole event.
Yeah, we can try
Okay.
this one.
Let's try that. Let's try to restart it. And maybe join again. Gentlemen, so we'll team number. So okay. Let's rejoin.
Mhm.
Okay, welcome back.
Hey, hey, hey. I can share my
Oh.
screen now.
So let's try it now.
So it was definitely a bug. Now we can confirm it.
Yeah. Okay, let's try. That it kicked me out. So
Okay, I see Brandon in the audience. Did I forget anyone?
I can see the screen. What about other people?
okay.
I cannot.
So still some people can't.
Okay, I think we should proceed now because all the screens will be available in the recording.
In the recording
Yep,
as well.
yep.
Yeah, you're right. Okay,
Yep.
so let's start, and I'm going to give you a walkthrough through the compiler and also the Sway. But I want to show you first a bit how the language looks like and feel like, because of course that's the complexity of the compiler itself. So as Brendan mentioned it, you can see here is for example a piece of code written in Sway. It's the option. It's the option enum, and if you walk through the code, through any piece of a Sway code, what you're gonna notice quickly that it really resembles Rust. So that's like my, let's say, the favorite part about it, having a blockchain language which with all these novelties of modern languages. So if you're accustomed to Rust and to all what Rust has in terms of a type system and so on, you will see that Sway code looks pretty much similar. So the enum is enum, struct is struct. You have all the nice things like impulse of traits. The traits are similar from the base library and so on. And in every like single piece of code, if you come in the doc comments and so on, it is very Rust-like, and it gives this impression of let's say general purpose language on one side. So you do not feel constrained by the language. Like if you want to express some, let's say, general thought in the language, you're in Sway really free to do so. That's on one side. And then on the other side, it has neatly integrated this other part, which means blockchain specific things. I will just show a few of them. For example, we have a concept of an ABI. That's the first class concept in the language, neatly integrated with the rest of the language again, and also very neatly integrated to that Rust-like part of the language. And it's let's say from the design side, one of the things I love about Sway is how let's say neatly the things are put together, like this general purpose part and also the blockchain part. So for example, so this is an ABI as an example, and I will just jump to, let's say, the contract which implements this ABI. Again, if you take a look at the code, you will see the things here like match expression, some, none, functions look, it's very Rust-like. But then on the other side, you have the things like storage, which is again a blockchain specific, and so on. So, and I think we have a good balance here between the expressiveness of Rust on one side, and then on the other side of blockchain specific things. And also, as Brandon mentioned at the beginning, what we aimed for zero costs, or let's say in worst case low cost abstractions, which then map to the blockchain. This is just a rough that you get a feeling how the language feels, and I want to go now through the compiler, and to help you a bit. Once you start investigating this part, I would suggest you to start from this document. So it's an internals MD, and you can find it in a Sway repository. So it's on a very top of the repository. Let me collapse this. We have a docs folder, and then within the docs folder, you will find this internals MD. I will not now go through the whole document, but it really points you to the part of the compiler where you want to take a look. If you really want to dig into it, I will show now the major parts and discuss the pipeline a bit. So if you are aware of a compiler design in general, here there should be no surprises. So our pipeline is similar to pipelines. Compiler pipeline is similar to compiler pipelines of many other compilers. So like we are chewing the source code, doing the lexical analysis, getting the tokens out of it, coming to the concrete syntax trees, abstract syntax trees, and semantic analysis. So that's the part. Yeah, I may be rushing too much. I will go a bit slower. So essentially, up to this part here, it's literally going through the text and making sure that it's structured in a way the Sway language expects it, and then the beefy part starts actually here. So the semantic analysis module is very rich because we literally supported things which Rust supports in terms of a type system. And so here is a lot of things going on where we actually type check mostly, or semantic check the type program. The second interesting thing is this intermediate representation, where we have our own intermediate representation, essentially a language of its own, which resembles to a good part LLVM. It's not the same. It has also, again, blockchain-specific elements. And on this level here, which I will show later on how it looks like, we do the optimization. So the major optimizations are done on the IR, like intermediate representation, and that's the main purpose of it. We have various optimizations. At the moment, most of them are those, let's say, typical optimizations of the source code. We still do not have many blockchain-specific optimizations, but that's the direction we are going in. And once we get the optimized code in the end, we are then generating the code for the targeting VMs. The Sway as the language is VM agnostic. That's the design decision from the beginning. At the moment, we are focusing, of course, on the Fuel VM. We have on this stage placeholders also for Ethereum VM. Mine is also there. But essentially, the code generation works fully nowadays for the Fuel VM. That's the pipeline. And as I said, I will not be going through the document. For each of these steps, you will find in this document literally where to take a look in the Sway code and how to start. I want to pinpoint the major things now where actually things happen. And also I would like to point you to the points where, if you are wanna get a part of this 1 million bounty pie, where it's likely to find something. I will come back to this graph later on and exactly point to those points. But maybe let's go through the code, at least the modules, and that you can map this diagram, those basic parts. So if we are talking about the repository, within the Sway repository, it's not only Sway. We have the packaging mechanism, the plugins, and also the language server. They are all here. Essentially, the Sway-related part are these packages, Rust packages, starting with Sway. So essentially, it's the IST core error and parse and type, and they correspond pretty well to the boxes you see here. So, for example, the lexicon analysis and syntax analysis are in the Sway IST and in the Sway parse, respectively. The IR part is in the Sway IR, and this middle part, the largest part, the semantic analysis, can be found in the Sway core. That's the part. So let's go then just some major structures and to major points where things are happening. So it's essentially, I will skip now the very beginning, the parsing, because if you're talking about the security from the security perspective, and the security issues and the costs of an issue, of a bug, if it happens, it actually, I would say, rises. I would say exponentially as we go right in the pipeline. So that means right here, we have fuzzing already, like bugs which are coming through, like nasty strings, Unicode acrobatics, and so on, will, in the worst case, result in a compiler panics. They will very likely not go through. But for example, bugs happening here, and I will come to a couple of examples later on, and especially bugs happening here are more difficult to find. They can result in a program which actually compiles, runs, does not revert at runtime, but doesn't do what it was supposed to do. Come to some examples later. So that's why I will shorten this part here, the lexical analysis, syntax analysis. Maybe just show you a simple thing. Essentially, for all the language elements, we have two traits. One is called peek and one is called parse, and they're actually responsible for the parsing part. Essentially, literally, chewing the characters, giving them the meaning, and so on and so on. And also building the stream of tokens, out of which we are getting something we call Lext program. And here I will come to, let's say, first complex part, where those Lext structures are actually turned into abstract syntax tree, which is still not type checked. Just to give you an idea here about the structures we get on the both sides. For example, the storage which I was showing here. Let me go here once again. You see that we have some storage element in the language. This line here, and after the parsing in something called Lext storage, the information about this storage element will be stored in a structure called item storage. And if you see this structure, it literally has, this string storage token. It has braces. It can have some annotations. It has commas, elements in the side, fields, and so on. So these structures are actually literally resembling the way how the code is written. And at this very stage, let me go back to the document. At this very stage, when we're coming to the syntax analysis, from lexical to the syntax analysis, we are turning that into declarations or into the parts which are parts of the abstract syntax tree. So what you can see here is now already a rich semantic information. So we have a vector of storage fields, we have the span, but we are losing the information about the formatting. We do not have, so it's not like high fidelity. We are losing like this where the comma was and so on. So this is the first, let's say, thing where a lot of things are happening. So for all the language elements in this stage, we are turning it into the abstract syntax tree. And then the second step, the semantic analysis, in terms of code complexity, definitely the richest one at this stage. You will find it in the semantic analysis. You can see here, I'm giving an expression here of a typed expression. So essentially, for all of those parsed elements, we have a type parsed equivalent. And we are type checking simply everything which we got. At this stage, we are building all the information about the types, about, for example, is it like does the trait implement what it should implement, and then everything which actually checks the semantics. And how it works, essentially all the phases, it's literally like top down, going through the hierarchy of nodes and trying to give them meaning. And what you can see here, the code will always look the same. We have something called type check context, which gives where we store the information about what kind of declarations we already have here, what kind of types we already have, what is known, and so on and so on, and then simply run through the nodes and try to type check them. So, for example, in this particular case, in this is the try to imagine this is just a array index. So I have array and then the square brackets and something inside. And here I'm type checking if the prefix, the first part is finally an array. Okay, that's that stage. And once that stage goes without errors, by the way, we bail out if there are errors between the stages. Once this stage goes without errors, we are generating the intermediate representation. To the intermediate representation, you saw the package like it's Sway IR, where you can find it. The logic is again similar. I will just go to function. Oh yeah, this one. This is again for all of the expression in the type check program. What we are doing is now we are generating the intermediate language code. So again, it's like going top down through all the through all the expression. For example, this is a typical tuple expression, you know, like open brackets, something inside, and then we are creating the IR representation of it, essentially the assembly code, which looks very similar to LLVM. Now, to give you an idea also from the other perspective, so this is how to enter into the compiler, into the code, and see where the things are. If you want to see the artifacts which compiler is producing, and that's definitely something I would advise to, you have the compiler itself will help you. So essentially, the compiler, you can run the compiler with the for command. If you install the fuel toolchain with fuel up, you can just run the fork, or here I'm running the compiler from the code, and just run the help on the compiler options, and you will see this, different options, which actually shows you the results of these intermediate stages. For example, ISM final will show you the finalized ISM. I will come to that, but maybe for this, what we are discussing now, just that you have a feeling for the intermediate language. If you say, build this project and show me the final intermediate representation, you will get on the standard output, essentially the intermediate representation. I will not go here into details, but it is documented in code, and we try to stick to LLVM wherever it was convenient. So what you want to get is, I have some script, and the script has an entry function, and these are the local variables in the entry function. All of those variables are structs, and then we have the entry block. It is the typical single static assignment approach. So that means we generate values, and each value is generated by an instruction, and so on and so on. As I said, check the command line, because you can play with this. You can see the IR after every optimization, and so on. So this part, compile, will produce the initial non-optimized IR, which means just go back to here. The initial intermediate representation that then runs through the optimization pipeline, which I'm going to show now. The easiest way to come to the optimization pipeline is to take a look at the pass manager. So how the optimization works. We have different optimization passes. We tried also to name them if they have their equivalent to LLVM. We try to name them the same as LLVM, and we register all the passes within the abstraction called pass manager, and then we simply run the optimizations. And if you take a look on any of the optimizations, let me go, for example, to function deduplication. Essentially, all of the optimizations are getting something called context. You can see it here. And this structure essentially holds the information about the whole program. You can think of it as having all this information, script, functions, locals, and so on in memory. All this information is stored in memory within this. Just to go back to the duplication within this context class. And the rest is, of course, going through the IR, recognizing patterns, trying to see what can be optimized, and so on and so on. The pass manager also holds the group to do all passes. So this is a good entry point to see what kind of optimizations we have and how they are organized and so on. And then finally, once we come to the final to the final IR, to the optimized IR, we actually generate the ISM, and to that we have ISM builders for different targets. As I said, so the fuel is VM agnostic. Also, the IR is VM agnostic, and then in this final step, we are actually targeting the particular VM. So similar approach again, another level. The ISM builder essentially interprets the IR and turns it into the final assembler. And for example, just to give you an idea, here on this level, we are literally dealing with that what Green showed, like how the VM works. We have to know the internals of the VM, the registers, the memory allocation, and all the other details. To give you a feeling for it, let me just run this. You can see the generated ISM as well. Let me just do it. So this is a simple, actually almost empty program, and you can now see what's really in the bytecode. This literally gets turned into the bytecode, which then in the final step gets executed on the virtual machine. Okay, so this was a high-level overview, I would say, of the major things to look at, and also where to find them in code. I would say this is definitely the entry point. Now to the bounty, to the bug hunting. So if I'm on your place, where I would look, as I said, the impact of issues which happen on these sites is, I would say, probably the highest. The optimizations are very difficult to reason about, and it's also difficult to formally prove that they're 100% correct. So the worst thing that can happen is that optimization will optimize something away or produce the code which does not have the same semantics as the original, but still works and does not revert at the runtime, which is, I would say, of course, catastrophic. As we move on the left, within the semantic analysis, most of the issues will if we have a bug, will in the worst case result in compiler panicking, or it will be the internal compiler error. But there are parts which are also tricky and difficult. So where I would look like definitely are the branching expressions, like the match expression. It is very, very difficult. And again, having a bug here, a semantic bug, could end up in like code running a wrong branch, which again would be catastrophic. Also, I'm talking historically about the places we had issues. And as I said, like here in this initial part, at least from my side, I I see less risk essentially. And as I said, we did already some fuzzings and fix some issues there. Good. That will be more or less that from the high level overview. I don't know, Brandon, do you think maybe should show something in additional testing maybe?
Brandon is not here.
Oh, Brandon is not here. So,
But yeah, you can show, yeah, like where people can run their test if they found something.
okay, yeah, let me show that. Maybe again to ease you to enter into the things. So this document definitely, and also as I said, play with the command line. Most of the artifacts we have and which are explained in this document. For example, we run that code analysis. So we have the dependency graph and all these things. The compiler will print those, so you can visualize them and so on. So, for example, let me just do this, that you get an idea. For example, what I'm talking about right now is the a DCA graph, for example, and these kind of things. So just to get a feeling for the artifacts which compiler does also internally, AST will print you the abstract syntax tree and so on. That will be the perfect way to start. And now to the testing. How we test each of the crates have cargo unit tests. But there are not that many. So we do test certain things. For example, in the optimizations which I was showing and so on. So these are like Rust tests, but we mostly rely on the tests which are here in this E2E VM tests project. These are literally end-to-end tests. That means they will run the compiler literally on the code and check for the expected output. And the way we are doing that, we have two major categories of tests. One is the should pass and the should fail. And for the should pass tests, let's say whatever, we have something here. We rely on asserts essentially. So we do whatever we want to test in the test, and then we rely on the standard library asserts that assert that the output is the expected one. And in the case of should fail tests, let me go for one. Let's say we have something here which is not valid. That means the compiler should produce an error. Those errors are cached within test toml files, where we use the file check to actually see if the output of the compiler is the one which we expect. So the compiler should render an error, and within an error we have to have these strings and so on. So we have the unit test, but most of the testing is done here. And we also have a special test for the IR generation, where in these tests we are literally we have different Sway programs, and then we run particular optimization passes on these Sway programs, and then you can see these checks, which actually check if the IR which is generated is the one which we are expecting. That's the, let's say, how we check the correctness of the compiler. There is an SDK harness which checks the correctness of the standard library, but that's, let's say, outside of it, outside of the strictly speaking, outside of the compiler area. Good. That will be the walkthrough. So once again, take a look on the this internal SAMD, and like follow the explanation, and also this very video on YouTube. I think would be definitely
Okay.
a good place to start. Yeah.
I think we can pass it to Rafael and touch bridge part.
Yep.
Right,
Thanks.
thank you.
Rafael, go ahead.
Yeah, can everybody hear me? Yeah, I think so. Share my screen.
Yep.
And Right, I think I have some troubles here.
Is there a problem with you sharing the screen?
Permissions. Yeah, I need to give permissions here.
Permissions in the Discord.
Yeah, the MacBook permissions for
Okay.
the.
Okay, I can't help you with your MacBook, obviously,
Right.
but
I
If
assume you need
can.
to
Well,
reconnect.
yeah. Wait. I know how to do this. Wait, just a minute. I think. No shit. All right, this is unexpected. Not sure how to give permission to this for screen recording.
Yeah, you need to open system preferences and go there to security and allow recording for Discord. And after you need to restart Discord.
So I'm failing to see where I'm there, but okay, here
Security and privacy.
it is. Yeah, okay. Okay, I need to reset Discord for this. So I guess that
Yep.
I will
Yeah,
back
maybe.
in just a second.
Okay, so let's wait for Rafael to join back. And yeah, like I just want to share, like in between, that this is like really cool that you guys presented the information from such a deep point of view. So like there's a lot of information to unwrap. I think it will help a lot. And Rafael is back. Let me invite him to speak. Hey, Rafael, welcome back.
Right. Let me check if this is. Yeah, I think it's done. Yeah. Okay. Can you all see me?
Yes, you're alive.
All right. So yeah, I guess that I will walk you through, as a smart contract lead on Fuel, I will walk you through the bridge repository, which is probably one of the yummiest places where you can find bugs because of both the impact and permanence of any issue that may happen on the smart contracts, the accessibility of its code. So I'm going to pass you in the chat the main architecture document that we have. And I guess that I would recommend that if you are going to go hunt for some bugs in here, you keep this open because it will help you navigate the whole repository in a very effective way. So yeah, to get started, I won't get out of this document, but just will give you some information about it. This repository is a PNPM mono repo. It has several packages. It's probably one of the best places to learn about Fuel because it has every moving piece, every cog, every wheel that you may find in the whole systems, because it either has the sources or npm packages or Docker files that will allow you to simulate the whole system on your local machine. And yeah, like as I said previously, you will be able to navigate most of the code from this document because there are links to every implementation, links directly to the code where everything is happening. I guess that to wrap this up quickly, I will just start describing how the whole system works from a user journey perspective. So here I'm going to start from the deposits, how a user can come and deposit any amount of ETH or an ERC20 token and have it reflected on the system. So here, you can see the user as the first component of this diagram that will send a message to the Fuel message portal. Fuel message portal is a Solidity contract that is obviously living on the Ethereum side, and he will be able to deposit any amount of ETH by calling this function, this send message. As Brandon explained at the beginning of this call, this contract will just emit an event that will be picked by the Fuel sequencers on the Fuel network, and this message will be directed to the user's wallet with a specific amount of ETH. Eventually, the sequencers will pick this emitted event on the Solidity contract, and this will be reflected as an UTXO on the Fuel blockchain. So that's pretty much it when it comes to depositing ETH. You will just call the message, the Fuel message portal, and any amount that you might be sending as ETH will be reflected as an UTXO on the Fuel blockchain. Then, when it comes to the to ERC20s, to tokens on Ethereum, the process is a little bit more complex. Here we talked about how the whole communication between Ethereum and the Fuel blockchain is in the end a message protocol, like a communication system between both blockchains. And this allows to basically have some entities on the ERC, on the EVM, and other entities on the Fuel blockchain that are able to send messages between them. And from a user perspective, what's going to happen is that it's going to call the Fuel ERC20 gateway. This is another contract on the EVM, and this will send a message again to the Fuel message portal, and this message is going to carry a payload and a recipient that will be the bridge predicate, which is as the name implies, a predicate that is living on the Fuel blockchain. This message will receive this message as an UTXO again when the sequencers include this with this event, and we'll be able to relay the payload and all the message contents essentially to the Sway contract that is the bridge itself, which contains this function, this process message functions that will essentially burn that message that was sent by the gateway before, and it will in exchange mint another UTXO containing the ERC20 asset that you have previously deposited. It's worth mentioning here that both when you deposit ETH and when you do this whole bridging process of an ERC20, the results are an UTXO with an asset ID, and all UTXOs in the Fuel blockchain have the same merits and the same privileges. So essentially, this means that once the asset is minted by this contract, the ERC20 bridge that is on the Fuel side, any kind of transfer or whatever you do with the UTXO that is generated has the same nature that as the ETH UTXO. So whenever you transfer any kind of token here, and that's one of the differences with the EVM that you might want to take into account, nothing happens on the state of this contract, because the UTXO lives with a already minted amount and asset ID on the Fuel blockchain. It lives separately from the contract. That means, for example, that you cannot pause transfers here as you could do with, I don't know, any centralized stablecoin like USDT or USDC that maintains all the balances inside the state of the contract itself. As again, maybe I would repeat myself here, but the UTXOs live independently on the Fuel blockchain. Once this contract mints that UTXO, then it's independent from anything else. That's from the deposit perspective from the user. Again, I will remind you everyone that you will be able to follow, like this document has a lot of diagrams that you will be able to follow, and it has links to the specific implementations of each action and how it happens in general here. So yeah, you will be able to check all of that from this document. Then when it comes to the opposite direction, when it comes to withdrawing and sending assets from the Fuel blockchain back to the Ethereum blockchain, the process is a little bit different, and maybe even you could say completely independent from the deposits one. So again, there is a difference between withdrawing Ethereum and withdrawing any other kind of assets. Here, the user starts as a withdrawer. In the case of withdrawing Ethereum, it will send a message out burning this ETH that he wants to withdraw, and this will be reflected on the Fuel blockchain as a receipt. And this receipt then will be eventually included via a centralized component that we have at the moment. Is the block committer. The block committer will be continuously reading blocks from the Fuel blockchain and pushing them in a summarized form, obviously, to this other contract, which is the Fuel chain state. It will keep pushing these block routes to this contract, and then you will, once that's happened, the user will be able to call the Fuel message portal to prove via Merkle proofs that this burn actually happened. And that's essentially when the Fuel message portal will unlock any previously deposited Ethereum and will release it back to the user. Again, this is all via Merkle proofs. The block committer will read the blockchain, the Fuel blockchain, and commit those routes in this state. Once the committer has committed the block, a timer will begin, so that it means that you cannot withdraw. You cannot prove that this happened immediately after the block has been committed. You have to wait a little bit for the block to be completed and finalized. That's when you can relay those proofs to the message portal and get your ETH back. When it comes to the to withdrawing ERC20s, it's a little bit different here. I guess that, okay, this diagram is actually incomplete, but you can get the picture. Like, the withdrawer will burn the assets on the same contract that minted them originally, and this will generate another message here in the Fuel blockchain. And essentially, you will repeat the process here. The withdrawer will be able to no, it's not here. So the withdrawer will be able to prove that burn exists on the Fuel blockchain activity. Eventually, the block committer will push those blocks into the state contract, and then you will be able to call the message portal to retrieve those assets as originally meant to. That's a very high-level overview. I guess that you can always follow all of these diagrams. They are very complete, and I think that you will get a very precise picture of how the whole system works. I guess that before finishing, I will just mention some key things that I think they are very important that you might want to look into. We do some downscaling of the of the amounts that you are going to deposit. As you may know, all amounts in both ETH amounts and ERC20 amounts are coded as with 32 bytes on the EVM, and they have like 18 decimals. Here, the interesting thing is, for the sake of state minimization, in the Fuel blockchain we operate with 8 bytes for amounts. So that means that whenever we have a deposit on the Ethereum side, we had to downscale that amount to 9 decimals and 8 bytes. So that's one interesting thing that you might want to look into, that we have all the math correctly implemented in there. Obviously, all of the smart contracts, except of the Sway ones here, the Sway bridge is not upgradable, but all of the Ethereum contracts are upgradable. So you might want to take a look into that as well, that we actually did everything correctly when it comes to upgradability. And yeah, maybe on a more abstract level, as I said, there is a communication between the let me check in here. Yeah, here in between the gateway, the ERC20 gateway in Ethereum and the layer 2 bridge on Fuel, there is a communication system in place. So that means that there is always some payloads coming back and forth between them in order to enable these deposits and withdrawals. That means that we have to parse the contents of these messages. And in the past, some other auditors might have found some issues when it comes to how we grab and ungrab these payloads, which is also, I think, a very interesting place to look into. Yeah, I think that's everything that I can say. Like, again, you can query this document at any time or ask me if needed. Thank you for listening to me. Appreciate to be here.
Thank you for such a deep dive. I think that will be very useful for the audience for the preparation to the hackathon. Guys, do you have any presentation that you will like to show us more, or we should go over like the questions and the topics we discussed earlier before the walkthrough?
Also, I'm not sure here. Like on my side, I don't have anything else to share.
Me neither. Yeah, we can go through the questions.
Okay, cool. Yep. So, like, I wanted to ask you if are there any things that you're feeling good about in terms of their security, and were all the parts of the Fuel network built from scratch, or some code was maybe forked from other projects?
I would say everything was built from scratch. Yeah, like we of course we're using some like publicly available libraries, like for example from client perspective, libp2p or rocksdb. But in terms of main business logic, I think everything was written from scratch.
Yeah, same on the language side.
So when it comes to the smart contracts, they are also built from scratch, and they are very adapted to the Fuel ecosystem. But I guess that you could say there is a heavy inspiration on what Arbitrum did. So maybe comparing to Arbitrum is generally a good idea.
Got it. Thank you, guys. And when I talk about the previous audits, like what are the most important bugs that you have received through the audits you had before, and which of them you really didn't expect to see?
I would say from client side, like most of bugs that we received were expected. Some of bugs was not expected because we was not expecting that we don't have test coverage for those use cases, because we discussed them and we discussed about them a lot, and later they was not covered, and during some refactoring we introduced some regressions. I would say something like this, yeah, because like I don't remember any super critical bugs. I mean, most critical bugs we found by ourselves, and all others was like, it's small problem, but it's fixable and shouldn't affect end user a lot. But again, it's like from client side. Maybe compiler had some bugs or breach.
Yeah, from the compiler side, so there were essentially two categories. One is where we are aware of things which we're actually already improving and fixing. So that's because the development is still like the cooling ground. There is a lot of things on the compiler which we're working on right now, and there were a category of findings which was simply the answer was we are working on that right now. It's in general like improving the infrastructure and so on. There were a few, and exactly in the optimizations, as I was saying, which were interesting, which were tricky. The things that simply skipped, for example, the way we hashed functions in the function, the duplication had collisions, so different functions were treated as the same, which is definitely a critical bug. And yeah, that was more or less it. There were a couple of smaller findings also on that side, and one important thing, but again, it's a cooling ground. This way, I didn't mention when the contracts are called, and in general, like on the boundaries, we encode and decode the data using our encoding and decoding infrastructure, which is new. And that's something definitely to look at. So in the example I was showing, these entry functions, for example, it's a new piece of infrastructure, very crucial. It's definitely somewhere to look at. There we got a feedback which was mostly performance oriented, but I'm curious also if there are things which are security oriented, which are there. Yeah, so much from the compiler side.
Right. Yeah, I think that it's important to emphasize that the compiler saw that recent revamp of the whole encoding, like the calls between different contracts and how the user calls and attach the payload for the calls. On the bridge side, we've had some findings in the past from auditors. I already touched on them briefly during my speech. May as well remind them that at some point we had some incorrect verifications and bad encodings of the payload between the messages that are sent for the ERC20 bridge, and also some very minor downscaling issues of the amounts that we encode. And that's pretty much it when it comes to findings on the bridge.
Also, I remembered something. During audit 1 year ago, our first audit, let's say we didn't have any plans to support 32-bit systems, but auditors pointed that in some places we don't follow that. And after that, yeah, we try to fix that, and now we hope we support that because now we actually have a use case for 32-bit systems. So I would say it was a nice recommendation from their side, and yeah, if people will see something that can work differently on 32-bit system and 64-bit system, then yeah, it would be nice if they will point out, because potentially it would be a problem for your network.
Thank you. Thank you for the insights. Okay, so maybe you have any suggestions to about what to look for in your code base, like from the perspective of the developers, like maybe some parts of the system that the white hats should pay more attention to.
Again, like we from client side, we have Fuel Core and Fuel VM. So on Fuel VM side, we hope we checked all places where we verify that you like verify memory ownership, that you can't write into memory of another contract, well, like into memory that doesn't belong to you, because that one can be a problem for other contracts, and later people can try to exploit it somehow. For example, overwrite address of recipient after smart contract call and something like this. So yeah, if they will look into that part, we'll double check that everything is covered right now would be nice. Yeah, like opcodes, well, like let's say all opcodes that somehow interact with memory would be nice if they will try, because we refactored the memory model several months ago to made it more cheaper for end user. So yeah, we try to review it, of course, as well, very well, and cover it with tests. But again, maybe people will find something. Regarding transaction validity, again, we hope that we included all rules that mentioned into our specification. And again, our specification mentions all possible, covers all possible malicious behaviors. But again, if people will be able to bypass those rules somehow, or they will see that that we don't have enough rules to cover some specific use cases, it also will be nice. And from field course side, let's say the most important thing is state transition function, like executor, and how storage works. So yeah, I would say that those two parts are most important. Maybe the next one will be like block importer that actually finalizes the state and verifies blocks and that execution is done correct. Blocks are linked, like all fields of blocks. Yeah, maybe from field course side that part, because all everything else it's more off chain. Even if there's something doesn't work, it's always possible to fix that. But if something is wrong with state transition function, it can be a problem for the network because it can require hard work or some recovery process to solve issues on that side.
Okay, thank you. So maybe you could answer. We have two questions in the chat. They're mostly focused on the Attackathon and how it will be managed. So the first one is there any standard severity classification of impacts defined for this kind of code, like virtual machine, core sway, etc.? We have at the Immunefi severity classification system. The user here is concerned that the same severity classification system cannot be applied for compiler or interpreter related code.
Like first of all, I think maybe Rafael has something that he wants to describe for bridge side, or maybe Igor has something to describe for compiler side. But yeah, let's answer first on that question and later come to them. So regarding that question, you will work with Immunefi to define severity and classification for different errors. So when Hackathon will start, maybe even before, I don't know regarding when it will be announced, but we have a table that covers all different aspects of the whole ecosystem, because we have a lot of stuff. So there will be definition of severity for bridge, for client, for compiler, maybe for SDK, for frontend, like for everything. Yeah, like they will be different, of course. But yeah, everything will be covered and clear.
Okay, thank you. Rafael, you wanted to add something?
Oh, I was just going to say that I don't really have much to add in that front. That probably for the smart contract side, you will be able to apply pretty much the same principles that you have been applying until now. So yeah, there's that.
Got it. Thank you. And there is a question from InfoSec US team about the known issues. So the compiler side is a work in progress, as mentioned by Igor. And if a bug is discovered, and internally you may have thought of it, how the known issues will be handled.
Yeah, so regarding that, again, before hackathon will start, we will provide a list of known issues by us. Yeah, let's say like we already, most of all information is publicly already available on GitHub, and if issue is publicly already available on GitHub and was created before hackathon, that it means that it already it's known issue. But we also have issues that are, we keep them privately because they can affect network. But we will disclosure them before start of hackathon, so people, you will see what are private, what you will see all our known issues. So if something that was discovered is not mentioned in the disclosure list and it's not publicly available, then it's new finding, and yeah, it's applicable for bounty.
Cool. Thank you, Green. Well, and since we don't have any questions in the chat, I think we can wrap it up. Thank you, Fuel team, for such a deep and informative presentation. I think it will help a lot of security researchers. Thank you all the audience who found some time to visit our stage and listen to this walkthrough. So yeah, thank you again, and don't forget to hunt on the Attackathon code, join the dedicated Discord server to ask questions directly to Fuel Network and Immunefi as you hunt. So yeah, thank you guys all again, and yeah, happy hunting.
Thank you.
Yep.
Thanks for
Bye,
inviting us.
everyone.
Happy hunting,
Thank you,
everyone.
everyone.
Bye.
Happy hunting.